For those of you who don't know, I'm Kayla Tormey. I'm a professor in chemistry, and this week it was chemistry's job to do the colloquium, which is why nothing's working right, because we do everything at the last minute and don't communicate, which is my fault. So we're going to have two presentations. One will be by a student, and then one will be by me. And so we're putting the good one first, so that if you fall asleep, it's at the end when I'm talking. So I guess we'll go ahead and get started. So this is Emily Harwood, and she's going to be talking about some of her summer research into hopefully all of your favorite subject, which is organic chemistry, and specifically malonyl radical kinetics. So go ahead and start.
Okay, so like Dr. Tormey said, I'm Emily. I had the opportunity of working with Dr. Truxa this summer, and we were working with free radicals, and more specifically the kinetics of the malonyl radical. So for those of you who don't know what a free radical is, it's an atom, molecule, or ion that has an unpaired electron. So normally, like in the valence shell, things like to be paired up, and so when there's only one, it is really unstable, and it usually is very reactive. It wants to find that extra pair, so the lifespan is pretty short-lived, so it makes them kind of tricky to work with. Why this kind of matters is that for further future implications, if we could better understand how these radicals work, it could possibly lead to us understanding how like free radicals can work in our bodies. So like I was saying, how they're pretty unstable, and they like to look through for other electrons. They kind of like scavenge through your bodies trying to find those extra electrons, and so they can cause damage to certain cells, DNA, and proteins. And so what Dr. Truxa and I were working on is to either support or disprove three different radical mechanisms: the Tanner, the Goldfinger, and the Bloomfield. And so in the next slides I'll show you, but the Tanner and the Goldfinger mechanisms deal with like a bromine free radical, and so that bromine free radical is what initiates the reaction and then keeps the reaction like pushing it forward, whereas the Bloomfield deals with the breaking of a bond to initiate it. So as you can see here, this is the bromine free radical, and so what it does is it pulls off this hydrogen to form this into the radical, and then that'll pull off this bromine, and it just is like a chain reaction that keeps going. And then similar to the Goldfinger, it also starts with that bromine radical pulling off the hydrogen, and then just a little bit different on the mechanics, but still the same concept. And so the Bloomfield is kind of where we looked at things. What we did was we added potassium carbonate to our solutions, and so what that did is it binds with the bromine, and it takes bromine's participation out of the reaction. So then we used an ultraviolet light on these solutions to break this bromine and carbon bond. So then once that is formed, you have these two different radicals, and so we were looking at trying to see which free radical does most of the work when these reactions are occurring. So for our method, we have our solution, and we add the potassium carbonate in the bottom. And so what we have to do is we have to get rid of all the oxygen. And so we put them under a vacuum, and we do this freeze thaw. So we get to play with liquid nitrogen, which is pretty fun if you guys haven't had to try it. But so we'd freeze our samples, and then we'd put them on the vacuum and pull out as much air as we could, and then we'd do that about 4 different times. We'd thaw it out and then refreeze and keep going. Once that's done and we can get the vacuum down as low as possible, then we seal them up by melting the glass so that the oxygen can't get in once we take them off. And so then we laid them at a slant with underneath this light so that we could maximize the surface area and try to get as many bonds broken as possible. And the reaction stayed underneath the lamp for up to 48 hours and sometimes even longer, depending on which solution you're working with at the time. And so previous studies that Dr. Truxa has been working with was when they used this potassium carbonate, the reaction didn't really have like a whole lot of product. And so the thought process was that either the lamp wasn't strong enough, or it was a combination of having the Pyrex tubes that they were using absorbing too much of the light, and so not enough light was getting through that barrier to break those bonds and like keep the reaction going. And so at the beginning of the summer, we used these quartz tubes and a different lamp, and what we found was there wasn't a whole lot of change. And so Dr. Trucks is going to give it one more try with a different lamp and then see if we can get some different results. But if not, that just kind of goes into one of our problems, that it's just a really slow reaction. And so that's just one of the things that you have to deal with, is that these reactions take a long period of time. So it's not like you can do a whole lot one day and then do it the next day. So it just takes a lot of time. And then another problem that we faced this summer was that we found some peaks that kept showing up in all of our results that weren't expected. And so one of them, Dr. Truxa had identified, and he can further go into that if you guys need, because it's freshly found out. But these other two are still unknown, and we are assuming that there are side reactions that are happening with that potassium carbonate and the diethylbromomalonate that we're using. And so one of the things is we're kind of like, well, is this side reaction affecting our overall reaction, or is it just kind of off doing its own thing and we're still okay to just keep going? So that's one of the things that we are still looking into. So moving forward, we finally started to test some different reactions a lot of this summer, which I learned about research is that a lot of it is prep work and figuring out what you need to do and how to do it correctly. And so we've already done a reaction with paraxylene and perchlorotoluene. And so what we do is once we have these products, after they've been under the lamp for their amount of time, we put them in a gas chromatography machine. And those can give us peaks that help us identify what our products are. And so we're furthering on and using these different reactions to get numbers to help us calculate the product that we receive, like the amount of product that we get from these reactions. And then those numbers are going to help us determine our rho values. So what rho values are is they're kind of like a measurement of how susceptible these different reactions are. And so if you look at this one, this is just diethylmalonate with sericammonium nitrate. So the sericammonium nitrate is what like initiates this reaction. So there's no bromine present whatsoever. And then this next one is diethylbromomalonate, and then using the light to break it. It's like that Bloomfield mechanism that I showed you earlier. And then the last one is NBS and the bromine free radical. And so the numbers should potentially be the same, but as you can see, they're not. And so since this one, which is the one that we're working with, is kind of in between these two numbers, we can kind of assume that there's a little bit of both happening. And so that was the purpose of adding the potassium carbonate, was to try and get rid of that bromine altogether. And one of the other things that we know about the NBS is that it has a tendency to like spontaneously just decombust and then like have bromine around. And so it was also thought that maybe the diethylbromomalonate is doing the same thing, which is what the potassium carbonate was also supposed to try and like avoid. So we're still working on that and doing some more reactions this fall, and hopefully we have more to tell. So is there any questions?
So are you going to try the longer term experiments with the UV light?
With like the different light, or?
Yeah, with the stronger light.
Yeah, so we have one more quartz tube left, and so as soon as we can get it to go, we have some reactions going right now, actually the perchlorotoluene. So once we get those done, we're going to try it out. So we'll see if it has any difference, then yeah, for sure we'll be using that. But if they're all the same, then we might as well just use the cheap ones that we have.
A lot cheaper to use the Pyrex.
Yeah.
So you said these reactions take a long time. Do you know which part or which step is kind of like the slow step? Is it the creation of the free radical that's taking?
Yeah, mostly the free radical, yeah.
Any other questions? Oh, then let's give Emily a hand. All right. Well, I'll introduce myself again. So I'm Kayla and I'm a chemist here, and specifically I'm a theoretical chemist, which means basically, according to my colleagues, that I'm not a real chemist. So that's fine. I'm also kind of a physicist, but according to my physics colleagues, I'm not a physicist either. And don't even get me started with the computer science department. They want nothing to do with me. So I just kind of do whatever the hell I want. And so that's what I'm going to talk about today. Originally I was going to have my students talk, but they didn't get back to me, probably on purpose. So hopefully in the spring they're going to talk. But I thought maybe what I would do is give a little introduction to one of the aspects of my research and what my students were working on this summer. And that is this two-molecule, what in the world? Can everyone see this slide? Is this all right? This two-molecule rhythm theory, which I have said as an alternate title, or why every molecule deserves a dance partner. And I found these things online. I typed in molecules dancing, and this came up. So you can find anything on Google. And apparently these things are called nanoputeins. I'm not sure. People have synthesized these though. So these are my dancing. I don't actually work with these at all, but they are dancing. So just a word of warning. I try to take out as much math as I can, but there's math in this. So bear with me, and I will try to walk us through this. I don't understand all of it, so I won't expect you all to understand. But any good talk, right? What's the first thing we have to do? We have to justify why the heck we're talking about it, talk about how we're going to change the world, right? I'm going to cure climate change and cancer and everything all at once with my research. Just trust me, and then, right, that's what we tell the grant people, and then they give us money, and then we fail, and the charade continues on. But my interest is in polymers and polymeric materials, so I thought maybe I'd take a minute to talk about maybe just how important polymers are to the modern world. And I'll take we'll use as our example a Tesla car. And for instance, one thing is in the paint, there's going to be polymers. The tires are made out of a polymer. The windows, while partially glass, are going to have a laminate on them, especially on the windshield, that's made out of a polymer. You're going to have plastic components as part of the drivetrain. You're going to have the most important part of the Tesla is what? The battery. The batteries use a special type of polymer mixture to conduct the lithium ions, so that's important with that. The seating, right, it has a polyurethane inside of it. That's what makes it spongy, so that has a polymer. So as you go down the list, every component in this single car involves polymers. And so our understanding of how polymers work and being able to rationally design, to understand, why it's doing what it's doing, and to design polymers with properties we want is incredibly important. Have I convinced you? That's good. Sort of. All right. Okay, so part of understanding how polymers behave, and actually molecules in general, has to do with something called the relative distances. So all the relative distances is if I have some part of the molecule here or an atom here, how far away is it from, on average, another molecule or atom, right? In gas molecules, are things really far apart or really close? Really far apart, right? And so that leads to the fact we can walk through this room, right? Not run into things. If they're very close, they're going to have a stronger attraction. They're going to be denser, so you can't walk through that wall. Now, as far as polymers concerned, how they're spaced, one thing that's of importance is thermodynamic properties. So, in polymers, if you take two different types of polymers and you mix them, they will sometimes mix together well, and they will sometimes not mix together well. They'll actually create little phases. So one phase of polymer A, one phase of polymer B, and they'll have little different shapes. So for instance, this is, if anyone's ever seen a hydrogen fuel cell, this is sort of how the Nafion electrolyte looks, where this is the watery section, and this is the Teflon backbone section, and you'll get a hydrophilic and a hydrophobic section. It'll make these little networks, and the networks will have different sizes depending on how you design your polymer, and they'll have different sizes depending on how much water you put in there, and that can affect how quickly the proton can transport or not transport, and that will lead to efficiencies or inefficiencies into your fuel cell, and that's all determined by what the polymer looks like and how it interacts. Structure, what the local morphology is. So for instance, depending on what you get on this surface, that can affect the conduction of protons. Kinetic properties. For instance, one thing of importance, I think still, this was when I was a graduate student, it was if you have a polymer as an electrolyte, you're trying to conduct lithium ions through this polymer. If you have a system like this, where if we pretend this is my positively charged ion and these are negatively charged, this will have some sort of free energy versus this one where it's completely surrounded. Well, if we need lithium to transport through the electrolyte, it's going to hop between chains differently if the distances are like this versus this, right? This, you can actually get more lithiums in because it's going to have be able to solvate it well, but this is going to have an easier time hopping across. And that all has to do with, well, what's the distance, average distance between this ion and the backbone on our polymer. Okay, so before we go, one thing that is of utmost importance when I'm doing my work is something called a correlation function. And a correlation function really is just a nice, handy mathematical way to handle distance information. So if you notice, right, I was showing you like, oh, this is this far from this is this far from this. This is nothing more than a function that says at this distance, the correlation is positive. So you'd have an increased chance of seeing another atom. Or the correlation function says, oh, this part is smaller, therefore you're less likely to find one. I'll have a picture here in a minute that I hopefully will make more sense. The nice thing is the correlation functions are going to show us how the atoms fit either really tightly together, more loosely, whether you always have atom A by atom B, or whether atom A and atom B rarely are very near one another. One huge benefit of looking at this in terms of correlation functions is, and as much as I hate to admit it, theory can't do everything. At some point we have to do experiments. And this is, these correlation functions can be confirmed with scattering experiments. XRD is one example where you can actually look at the spacings of things in a solid or in a liquid. Typically the way we look at this is something called the radial distribution function. It's a big word, but it's actually not that complicated. And it's usually just referred to as the RDF. And if we have that, and we have the pair potentials, we can actually get all the energies of the system we need, right? If we know how far things are apart, and we know what the energy is for two things at a certain distance, we can figure out what the total energy of the entire system is. So here's an example of a pair correlation function. G of R, this is just shorthand for the radial distribution function, and H of R, and they are related through this. I know you guys understand this equation. So it's the radial distribution function minus 1 is what's called the total correlation function. Don't worry, there's even more names. But this is the basic idea. If I have, for instance, a sodium ion in a liquid solution of water, the sodium ion is positively charged, therefore it will attract the water molecules, oxygens, right? Because those are partially negative, and so you're going to get a clumping right here of water molecules. And what we can see right at the very, very core of the sodium, if we were to ask basically, what is the probability of an oxygen atom being a certain distance from a sodium? Inside the sodium, we would expect the probability is 0, right? They're not going to cross over each other. And then what's going to happen is as we leave the sodium ion, there's going to be this shell right here, right? This is really three-dimensional. I'm just showing a little slice where you're going to have a huge probability of finding water molecules, right? You're going to have a bunch of them, and they're going to be in a very small volume. So you get a huge peak. So that's what that's saying. It's saying, okay, a little ways away, we're going to have a lot of water. Now this water is going to keep other water molecules away. So what's going to happen? The probability of finding another water molecule is going to go down until you get to this one, where you have another shell where these waters, right, are going to be attracted to the hydrogens. And so you're going to have another spot here where you have an increased probability of finding a water molecule next to a sodium. And then, I don't have it in the picture, but you could imagine another shell where we have another one. And then eventually, right, it's going to kind of dissipate, and then you'll have water more randomly oriented. And these are called, I don't know if you probably don't learn about these in biochemistry, not to put you on the spot. These are called shells of hydration around ions. So this is the basic idea behind the radial distribution function, is looking at, at a certain distance I have an increased probability, then a decreased probability, increased and decreased. Okay, so we can look at how much structure is in a liquid, that's what I care about, are liquids, by looking at, right, how high and sharp the peaks are. So in a gas where things are very far apart, there may be some correlation, a little bit, but right, it's going to be kind of smeared out and not very strong. And so you'll get a little bit of increase and then a little bit of decrease, and then it'll just kind of go out to whatever, the normal average density would be. In a liquid, things are more tightly packed, but right, they can kind of move around a little bit, so it's going to be it's going to be more sharp than a gas, but also kind of smeared out, and so you're going to get that sort of look like this, where this is showing some structure in here. And then if we go all the way to a solid, especially a crystal, things are spaced at exactly even patterns, right? That's what makes it a crystal, and there we're going to get very thin, narrow lines where things always are found. So we can see with increased packing, we get sharper lines, as well as with increased amounts of structure. Okay, so liquid state theory. What is a liquid state theory? The whole point, literally the whole point of a liquid state theory is, if you tell me the potentials, so how two things interact, whether they repel or attract or do a combination of the two, I want to know how they're going to arrange themselves, right? That would be super convenient, because what I could do is say, oh, well, this has a +2 charge, this has a -2 charge, they're about this big. If I get a whole bunch of them at a certain density, the liquid should look like this, they should pack a certain way, they should be a certain distance from each other, and from there, right, then I can know things about how they might phase segregate or different properties of the system. So that's the goal. I want to know how they interact, and then I want to see how they arrange. The most successful theory to date, I hedged my bet with one of the most successful, but I think it's the most successful theory, liquid state theory to date, is something called reference interaction site model. And for short, it's called RISM. And it has been applied to polymers, which is actually what I end up using in most of my research, and that is actually just called PRISM for polymer reference interaction site model. But biological systems, it's used for understanding, for example, how nanoparticles will arrange themselves with polymers and all sorts of different things. It's an atomistic theory, The nice thing about that is, if you recall, packing was important, or how things would arrange themselves. This doesn't average out those things. It actually takes the structure of the atom as an important fact, and so you can actually get a lot of important information out of that. One problem is it doesn't handle very attractive potentials well. So it's good if you pack a bunch of things together and they're repulsive, they're not very attractive, but if you kind of let it relax and they're slightly attractive, so for instance in water, where a Coulombic potential, right, is really strong, it doesn't give great results. The theory is based on the correlation functions, and it won't capture multi-point correlations. So it's just one thing to one thing, not where you have like A, B, like A and B to C. So there's some limitations. Okay, I promise this will be the most part of the math. So this is something known as an OZ theory, and here's the basic idea. So more correlation functions. An OZ theory states this. If I have particle 1 in the dashed here, and I want to know what's the probability of finding particle 2 at a certain distance r, right? That's all the total correlation function is saying. If there's no correlation, it will be 0. If it's a big number, or if it goes more, it will be a case where you have something that is more likely to find it or not. What we can do is say, here are the ways we know this thing is influencing or influenced by this thing, and the probability. This term, C of r, is called the direct correlation function. And that is just, how is this directly affecting that? And that's right here. So we can see, if we want to know the total correlation function, what is the direct contribution? Well, that's one way, right? The problem is there's all sorts of other crap in there. So we can also say, well, what about the influence of this one on this one? That would be this other direct correlation function. But I don't care about this one to this one, right? I care about this one to this one. So what I can say is, well, what's the influence of this one to this one, and then this one to this one? So that is an indirect contribution to the correlation of this to this through that intermediate particle. Does that make sense? Then there's an additional one, right? There would be this one to this one to this one to this one. And you can imagine, right, this would go on for infinity for all the possible particles that are in there. This term takes into account all the indirect ways one can go to 2. And if you look at this, any of the math people, what does this sort of look like? Yes, a Taylor expansion. So what do we do with a Taylor expansion? We chop off the stuff we don't care about because we don't care, it's higher order. And that's how we end up getting these OZ theory equations, which RISM is one of. And we'll get to that in a minute. Now, what's nice is, this means all I have to do, I don't have to describe H of R, the total correlation. I just need to have an accurate representation of those short-range interactions. If I have those, this will account for all of that and give me some reasonable result. That means I need some way of describing it, and that's what's called a closure equation. You don't need to know what it is, other than this tells me something about how this influences that, and then propagated through indirect interactions. Okay, if we take this equation, this would be for atoms, right? An individual atom. The problem is, if you have something with lots, like with a molecule, right? I can not only influence, so for instance, if I was to look at the influence of this one, or I guess I'm doing here, this one to that one, right? It would have those intermediate direct correlation functions, but I could also influence it through the chain, right? So this one could influence this one to influence that one. So we introduce another term called the intramolecular correlation function. That's the last one. That's the last correlation function for the rest of the talk. And so if we generalize an OZ theory to account for the fact we not only have direct correlation functions between things, but we also have intramolecular correlation functions within things, you end up with this, which is the rhythm equation. Now, if you notice, I have these little stars here. Does anyone from math know what a star does? Even advanced stats probably uses this. It's called a convolution. Nope. Damn. I thought somebody would recognize it. That's all that is. That's a convolution. It's a type of integral. Don't worry about it. It's a special math thing. Don't worry about it. Okay. Now, the benefit of using convolutions is that if we take a Fourier transform, all of our matrices or all of our terms are multiplied. That means we can just use algebra. That's all you need to know about that. We can use algebra, makes solving it super easy. It does, however, mean we need some way of knowing what the intermolecular correlation function is. There's several ways to do it. There are different models. You don't need to worry about them because I care about simulating it. And when we simulate it, we can get some fairly accurate results. And then we also need the closure. If you remember, I need to know how the direct correlation function looks between two things and have some approximation of that. Okay, so here's the basic idea. What I could do is rather than simulating a whole bunch of molecules, I could pretend this. I could say, okay, one of my molecules is going to exist here, and this is just a bunch of other polymer molecules. And there's going to be the internal energy, right? The fact that the polymer can bend and change and twist, right? That will have some energy. And then there will be the energy of it sitting with the other polymer molecules. The issue with this is that's a lot of stuff to keep track of, and I don't want to do it. So what I can do is say, this I can handle. I can handle one polymer simulation. And I'm going to approximate the rest of these with this thing, this WR thing, which I'm going to call the solvation potential. And all that is saying, let's pretend there's a whole bunch of other stuff in here, and we do it by just basically just adding an energy term. That's it. The benefit of it is we can get this by solving the rhythm equations. And that's, right, we get this from rhythm, this from the simulation, and this from our closure relation. So we plug that into the rhythm equations, get our solvation potential, and we can do a one-chain simulation. And the simulation will generate our omega, which we need for rhythm. And rhythm will generate our solvation potential, and then we can do this back and forth until we get to a solution. And this is the one-chain solution. So here's my one chain. Here's my chain with a bunch of other chains. I'm going to simulate it, and basically you just run a simulation, you solve the Prism equations, and then as you solve the Prism equations, you get a new solvation potential, and you just kind of keep doing this over and over and over until your chain looks supposedly correct. Don't worry, I'm getting to the dance partners soon. Because if you notice, this chain is dancing by himself, or herself, I guess. And that's going to lead to problems. And here it is. So, if I look at a one-chain simulation for polyethylene, our gold standard is molecular dynamics simulations. These are large simulations with thousands of polymer chains. They have to be done on supercomputers, so they're super expensive and, not practical. They are if you're at a bigger university or something like that. But they take a lot of time and a lot of energy. So we consider these correct, and they're pretty close to correct. If we look at this one chain, so this dance partner dancing alone, and he's being simulated by himself, we notice that the shapes for a polymer of 66 monomers, so a longer chain, and then a shorter chain of 24 monomers, they look close. So the MD simulation is in blue, and the rhythm solutions are in green. But you notice the one-chain solution is much shallower. It's less structured, right? That was one thing we learned is as you get bigger, tighter peaks, you're actually getting a more structured material. A more structured material, if you're talking about, for instance, blending polymers, will have different properties. And so you would inaccurately predict, for instance, phase segregation in the polymer itself. So this, while not terrible, we want it to be better. And this is where we introduce a dance partner. So what we do is same thing, right? if we'd have this big simulation or a big bunch of polymers with a bunch of chains. We pick 2 of them, we pull them out. We're going to approximate the rest of these chains with solvation potential, but we're going to do things slightly differently. We're going to have a 2-chain Monte Carlo simulation, so we're going to have the 2 chains simulated together so they can interact with each other, or dance if you will. From that we'll get our intramolecular correlation function, right? That is how it's shaped, how things are influenced within a molecule. And we'll get, this time we don't have to rely on the rhythm equations to give us either our radial distribution or our total correlation function. We can actually get that from the simulation itself. And this is the key, because we want to get really accurate information when things are close. We're going to actually extract this from the simulation. We put this into the rhythm equations. It then gives us information for how this would look if it was a whole bunch of polymers, and you do that again over and over and over and over and over until you get supposedly an answer. And here's the result. Here's the MD result again. Here's that 1-chain result again. And now in red, we have the 2-chain result. And you can see, just by having one other molecule in the simulation, so by this chain having a dance partner, look how much better that is at approximating how they would separate themselves in a solution. That is astounding. Well, you may not be astounded. I'm astounded. All right. This is great, right? This is wonderful. This is great. This was all done. I did none of this work. Because turns out there's a really big problem. The motivation. So, all the work I showed you using the rhythm equations, remember how I said we could just use algebra to solve them? We can, if we only have one site type. So if every monomer is the same time a monomer, works perfect. That's super boring and not helpful, because most polymers are not made that way. They're made with 2 types or 3 types. And if you do that, what happens is you end up having to use matrix equations. And matrix equations, you don't use algebra the same way you use linear algebra, which means there's some weirdness. Weird things can happen. And the weird things that happen are you're going to see here in a minute. So my goal was to start with a simple thing. So I'm not going to start with polymers. I'm going to start with super simple little molecules and see if I can get something, see if I can improve my results. So here's the problem. If I have, this is the simplest molecule I can make, right? A dimer. So if both sites are the same, A types, it's a scalar equation. It solves easy, right? Everything's good. You can see when I solve my rhythm equation, this is just all, the C new, all that is me solving the rhythm equation from my simulation stuff. We can see we get this nice smooth line. If I instead though use my simulation with a heterodimer, where even if I define these as having the same size, the same properties in general, but I just label them differently. Literally the only difference is I call 1A and 1B. I end up with matrix equations. I get this divergence behavior. You can see this, right? That's ugly. That's horrible. You can't solve that with a computer. It blows up. You start getting not a number and, you know, things in the quadrillions. It's horrible. Okay, so this is what I actually, finally we're around to something I do. So, what happens with the divergence? So, when we're calculating this, so this is just solving the rhythm equation. I have to do a matrix inversion. And to do a matrix inversion, I have to calculate a determinant right here, right? So this is, you flip those things, and this is just a matrix inversion for a 2x2 matrix. I have to do a determinant, which is AD minus BC. What do you notice as this starts to get to small values of K? What does it approach? This is 1 over 0. That is not a good thing, right? So as this gets really, really small, this explodes into something really big. Now, when you do this analytically, it turns out this part, so the Fourier transform of the total correlation function actually becomes really small. And it will cancel out that thing becoming really big. And so it all works great. The problem is when you do a simulation to collect your total correlation, or your total correlation, there's noise in it, right? So it actually doesn't perfectly cancel. This won't perfectly cancel that because of some problems with the simulation. And so you end up with these divergences and you can't solve the problem. You can't use a computer to solve it. So this is what I did. I took the brute force approach and said, I'm going to just add a little number to every single one of my simulation points. Then there's a ridiculous amount of math I'm going to do that I did not put, so be very thankful I didn't put it in the presentation, that in effect is going to project, or I prefer to use the word, it's going to filter my simulation so that it behaves. I'm saying, you need to act analytically. You're not acting analytically, so I'm going to kind of ooch you along until you act analytically and you act correctly. And so that's what, and so this should project out the problem. And it worked. So this is the raw data. I do my little tiny addition of little tiny numbers in a rational way. I didn't just randomly do it. And you can see I get this nice smooth line that matches the scalar equations. Great, I'm done. I get my PhD. Let's leave. No, this is where I not warn people about getting a PhD. Solving this problem, this to this, took me 2.5 years. Yeah. So there's a reason your professors are a little odd. So anyway, yeah, I was having nightmares. Like, I am never graduating. My advisor's going to kick me out. And this was a last-ditch effort. It was this sort of, I went, what if we try this? First, like, why don't you try that? And we sort of came up with this plan just randomly one day in his office, and it worked. Okay, so just to kind of show it, so the raw data is in red. It's probably hard to see. You can see I don't tweak it by very much. It actually it just sort of raises all the points. And one way you can tell that it's working in the correct way is if we look at the Fourier transform of it, the majority of the correction is happening at low k, right? That's also where the divergence was happening, right? That's where we were getting the big divergences. So it's fixing it in the right spot, not fixing it further out. Okay, so linear hard spheres. So this was one of the systems I tried. It's just 3 spheres in a line. I also did bent, but the results for this were pretty interesting, so I'm going to present these. This just means these are the ends, and this is the middle. So we can look at radial distribution functions for, an end to an end to a middle, or a middle to a middle, right? Those would be the 3 combinations you could get, because the other end to the other end, those are degenerate, or they're the same thing, basically. And then what I treated them as hard spheres. All that means is that they either don't interact, they have no attractive or repulsive any distance. You just can't put them, you can't overlap them. That's just, it's not allowed. And that's enforced in the simulation. And we're going to do a range of densities. All you need to know is that the density is increasing this way. So it starts at the 0 density limit and goes to a more dense state. And then the bond length between each thing is 3.93. And the sizes of these are 3.93. So these are what are called tangential spheres. So this is the 0 density limit. The yellow line is a 1 molecule rhythm, right? No dance partner. And the Monte Carlo is the blue dot, and that's the one we care about. That's the quote-unquote gold standard. This is what we're shooting for. And the green dots are my results for where I have a molecule with a dance partner. So you look at this, and it matches exactly, which is amazing, except that in the theory, in the 0 density limit, it should match. It should be exactly the same. So this is good for proving that you know what you're talking about, but little else. If we increase the density, though, we see, look, the one molecule, if we look at the Monte Carlo, we end up with something that looks like this. The one molecule has a similar shape, but look, this cusp is further down. So how it's looking end to end between 2 molecules, it's actually not predicting, it's saying it should be further out than it is. It should be closer. That could have ramifications for how the things behave in bulk. Same thing here. This is similar, but this is saying, well, there's sort of this recovery here. And this, both the simulation and my results say, no, it should die out. And this looks like middle to middle was pretty close, increasing the density further. Again, we see both of them predict a cusp, but mine predicts the cusp in the correct spot. Again, look, the simulation has a little structure even here in between this part and this cusp, and mine overestimates it, but also predicts it. These actually look pretty similar for all of them. This, again, this predicts some structure in here. Mine predicts the same, shifted a little, and all three predict the cusp there. And this should be I think this is the densest state. And again, you see, as you go out further, they're fairly well in agreement. This one, the middle to middle, they're also in fairly good agreement. This one's pretty close, but again, there's a little bit of structure here that the simulation, or the Monte Carlo, which is supposed to be reality, predicts that mine does, and the one molecule doesn't. So just by adding that one molecule, you gain that information back. So, conclusion. There was hopefully some successful development of this two-molecule rhythm theory. So this was supposedly my contribution to science, which is why they gave me a PhD. And this is a new theory. It's shown high accuracy for these short-range interactions, which way back at the beginning of my presentation, I said for polymers, right, could lead to really important properties. The numerical efficiency versus simulation. The hope is that this is faster than a supercomputer, and you could do it on a desktop. That has yet to be shown, but that's for other reasons. And one nice thing, I didn't show you this here, but I could do this for Leonard Jones attractive potentials, but even more importantly, I did this with water, which is a really strong attractive potential with a Coulombic potential, and it also showed better results than the single molecule rhythm results, and was able to converge, and so I was able to capture these attractive potentials. There's a bunch of different models for that solvation potential, right? The thing that approximates the other molecules. It doesn't really, some of them didn't work numerically, like it just wouldn't converge, but for the most part, the answers look the same. And then the repulsive and the attractive gave better results. Future work. So we want to move beyond, and we have moved beyond just linear, set in stone molecules. We want flexible things, right? We want polymers. We want oligomers, things that are more flexible. So we're in the process right now. The work over the summer was actually writing more software for doing these polymer simulations. Then we can actually look at blends. We can look at two different polymer types and see there's been a lot of simulation work done. So for example, one thing you may not be aware of. So polyethylene used in water bottles, that's the same polyethylene that's used in plastic bags. The difference is some of them are long and some of them are branched, and then they blend them. They basically take two different polyethylenes with different structures, blend them, and you either get something that's hard or something that's really thin and flexible. And that all has to do with how miscible it is and that short-range interaction. And then ultimately what we'd like to look at is how ions can conduct through a polymer, right? Because if you get the shape of the polymer right and how far away they are, you can predict, well, what's the likelihood of a polymer or of an ion hopping back and forth, and you can hopefully make predictions on how good of an electrolyte a polymer would be, for one chain versus another. And any questions? Yes.
Just wondering.
Yes.
You were a chemist when you graduated here.
I was a chemist. Yes.
Yeah. So how much and why new math did you have to learn in grad school to be able to take on?
So the question is, how much math did I have
How
to?
much and why did you learn new math?
An enormous amount. It was just a lot. Yeah. I mean, the thing is, math is very hierarchical. So it's not like all of it was new. A lot of it I knew. It was just you're applying it in a new way. So for instance, how many of you have had differential equations? Okay, so quite a few of you, right? Have you guys done integral equations? Yeah. It's just, I had never encountered integral equations, so I had to learn about integral equations. And RISM is an integral equation. So rather than, finding the function that satisfies it, the derivative, you find the function that satisfies the integral. And so just like with differential equations, right, you learn the majority of differential equations are unsolvable. You have to use computational methods. That a lot of what I was learning was, well, here's how it should work. Here's the numerical way you actually solve the integral equations. Yes.
So is there any possibility that in the future that this kind of modeling could be used to look at self-assembly of biomolecules, like protein folding or lipid bilayer self-assembly, or maybe even substrate in an active site?
Yes. It could. Yes,
Yeah.
absolutely. There is work where they look at that. It's something called three-dimensional RISM. There is still a possible issue using just the regular RISM equations, in that what can happen for something specific, like if you're talking about like a protein with a ligand, especially if the ligand was charged, is that if you assume that it's isotropic in every dimension, you actually would not get the dielectric correct, right? So it might be more charged or less charged, and so it can lead to some funniness. There is another version of RISM called dielectric RISM, and then the 3D RISM, which could help. So I'm going to say yes, it could, but I think a lot of work would have to be done for this 2-chain to work correctly. Yes.
So would you do it on the simulation in a supercomputer?
So the large molecular dynamics simulations were all done on a supercomputer. It was at Colorado School of Mines, and so they had a big supercomputer that's now moved to somewhere in Wyoming, and then they share it with the Department of Energy, I think. Or no, the atmosphere. I think they share it with NOAA. But yeah, those ones, and it's kind of one of those frustrating things where the bigger simulations, actually you can start doing them on smaller supercomputers. One of the issues is you have to approximate these polymers as much shorter than they would be normally. Usually you'd want a chain that's like thousands of monomers long. And we do something that's 66, which can be inaccurate for some things. So one thing the 2-chain would do is that because you're not scaling by a cube, because if you're going to do something 1,000, like you get this weird, it's not a cube, it's like n squared. This would not scale that fast, and so you could actually recover some of that simulation efficiency that way.
So what was the hard part?
What was the hard part?
Yeah, so what was the hardest thing that
What was the hardest thing?
yeah, I mean, what was it that, was there like something that was like you got it and then that finished, or was it just incremental over 2.5
It was,
years?
well, the hardest part was solving that divergence problem. Mostly because we knew exactly why it was diverging. Like you can do it, right? So you do it, this is for all you physicist students out there. You do a Taylor expansion, you multiply all your equations as in a matrix thing, and then you look at your Taylor, the power terms for your polynomials, and you could see exactly why it was diverging. The question was, how do you take your simulation data and fix it? Like, you know the conditions that have to happen to fix it, but how do you do it the right way, if you will? That was the hardest part. And this may not be the best way to do it. I have a feeling some mathier people, statistician, whoever, would look at this and go, dude, there's this one thing you do, and everyone's known about it forever. You didn't read a book, and sort of thing. But yeah, but it was getting that to work. That was probably the hardest part. The next part was once we figured out how to do it analytically, like on paper, it was then how do you do that in the computer, because you end up with these really big equations, and
That was gonna be my next question, is how much, and you asked about how much math, but
It's-
how much computer programming did you have to figure out to
A
to do
lot,
this?
a
Yeah.
lot.
Yeah.
But, I mean, you have 6-7 years. So
Yeah, that's right.
even I can get moderately mediocre at something in 7 years. Yeah, that was the frustrating part was that my advisor is hands down by like orders of magnitude the smartest person I've met, and so I'd always go in and have some question, and he would solve it in, a tenth of a second. And he was kind about it, but I could tell, like, this guy is an idiot. Why did I let him into my laboratory? Well, I think there's 2 minutes, but I'll end it early if you want. All right. You don't have to, I won't thank me for speaking.